everyone. Welcome to part 2 of our lecture on chemical kinetics. So we're going to continue chapter 14 from where we left off. Today we are going to talk about a way to measure reaction rate. We're going to look at different factors that affect the reaction rate, and then we're really going to get into determining the order of a reaction with respect to certain reactants, and then determining a rate law as well as the value of the rate constant. So lots to get through today. So first off, like I said, we're going to look at ways to measure a reaction rate. Sometimes you can look at a reaction. There's things called clock reactions, and one of them is the iodine clock reaction. It will go from completely clear to completely black, and you can see like the reaction is done. It was clear and it's black like in an instant. It's really neat. But not all reactions are like that. Some will react more slowly, right? The concentration, right? Say we were measuring a copper solution. Maybe it got more blue over, a period of time. So we can actually measure the reaction rate by measuring the concentration of one of the components, right? We can look at the concentration of a reactant and see how that concentration is decreasing over time, or we can look at the concentration of a product and see how that concentration is increasing over time. Some reactions, like I said, will occur slowly enough that we can actually go in and take samples periodically and analyze them and see, is our reaction done or is it still going? How quickly is it going? All of that kind of stuff. One common technique is spectrophotometry, and this measures the amount of light that's going through or being absorbed by our solution at a given point in time. So this is what it would look like. So we would have some kind of a light, right? And then there's a slit, and that light gets sent through a prism, okay? And the prism will split the light. We learned this last semester in Chem 1, and it will split it in all colors of the rainbow. And we can use what's called a monochromator, and that will select one specific wavelength. Okay, so far we've had our white light, we split our white light, and then we have the monochromator that picks one of those wavelengths, and that is what we're going to send through our sample. So this is just one specific wavelength that's going through our sample. And we're going to look at how much of that light our sample absorbs. So our sample here is typically going to have some kind of color to it. Maybe it's blue, maybe it's red, right? But it's going to be colored so that we can look at how much light is getting through. Okay, if it was a clear solution, all of the light would go through and it wouldn't tell us anything about how the reaction is going. So in this example, we would need a colored solution, something that's going to either get darker or lighter over time as the reaction proceeds. So then we have this detector, and that detector will collect the information regarding how much light has gone through, and that will we can use that to figure out our concentration. Okay. So when we start looking at concentration versus time data, and that's actually going to be, in the next lecture that we're going to look at this data, this is how it's collected. Okay, this is how we would get this concentration over time. There are other ways of doing this. You can use a gas chromatograph, and you can use a polarimeter, right? And they all measure different things, but they all go with the same kind of philosophy that we're going to use something to measure the amount of concentration change over time. I'm including this as the example because I think it's the easiest to think about. And also, I plan to do a lab in which we are going to measure our changing concentration over time and relate it to either our equilibrium constant, which we'll learn about in the next one, or our rate of reaction. Okay, so this is really commonly used, especially at this level of chemistry. Okay, so some factors that can affect the rate. We talked about concentration last time, right? Because like I said, concentration has a lot to do with our reaction rate because we're going to think about our reaction in terms of collisions, right? So if we increase our concentration of our reactant, we're putting more molecules in there. And if we put more molecules in there, they are more likely to bump into each other and cause a reaction. So typically, increasing our concentration usually increases the rate of the reaction. There are some instances where it doesn't, but most of the time, if we increase the concentration rate, we are increasing the number of collisions that can happen, which increases the rate of the reaction. Increasing the temperature will always increase the rate of the reaction. So if you want your reaction to go faster, bump up the temperature. That's really easy. Unless you have something that is temperature sensitive, like I alluded to last time, sometimes if we increase the temperature, it can make a product that we don't want. So, be aware of that. But usually if we increase the temperature, we can make our reaction go faster, and then we don't have to sit there all day staring at it. And it will always increase the rate of the reaction for two reasons. One, our particles will collide more frequently. Again, if we're thinking about our reaction in terms of collisions, right? If we increase our temperature, our molecules are moving faster. And when they're moving faster, they can collide more frequently because they're moving faster. They will also collide more energetically. And this will be important in a later lecture in this chapter. Right? If we increase our temperature, we are giving our particles more energy. And in order for this reaction to occur, our reactants need to have enough energy to make the reaction go. It's not enough to simply have these molecules bump into each other, but they need to bump into each other with enough energy. And that amount of energy is called the activation energy. So if they don't have that, they don't have the minimum amount of energy, right? They don't have that activation energy. They'll just kind of hit each other and go on their merry way. So we need them to have lots of frequent collisions, and we need them to have very energetic collisions. So increasing the temperature serves both of those purposes. If we increase the surface area, we will increase the rate of the reaction. Again, this goes back to the collisions. And by increasing surface area, I just mean crush it up. Is essentially what it gets down to, right? If you think of sugar, okay, so think of a sugar cube versus normal granulated sugar. If you were to put that sugar into, your coffee or your tea or whatever you're having, right? The granulated sugar is going to dissolve much more quickly because it has a larger surface area, right? It's all broken up. So those water molecules can collide with the sugar molecules and dissolve it really easily. If you have your sugar in a cube, it has a very small surface area. So the water molecules can only dissolve the sugar that's on the outside, right? And they'll take off that layer, and then they can dissolve the sugar underneath. Well, the same kind of thing happens with our reactions, right? If we have a very small surface area, right, our collisions can only happen with the outside molecules. So we want to increase our surface area to increase our rate of the reaction. So essentially, crush it up. And then the presence of a catalyst. We'll talk about catalysts at the end of this chapter, but catalysts lower the activation energy. They lower the amount of energy that these reactant molecules need to make the reaction go. And the way that they do this is they provide an alternate pathway. The reaction happens in a totally different way than it normally would. Okay, so and that other pathway has a lower activation energy. So that's the purpose of a catalyst. So these are all of the ways that we can affect the rate. We can change the concentration, change the temperature, change the surface area, and add a catalyst if we need to. Okay, so we're going to look at concentration first. The rate will often depend on the concentration of one or more of the reactant molecules. And so when we are describing this rate, we will write a rate law. And they will express the relationship between the concentration of the reactants, right? So how much is in there, and the rate of the reaction, okay? And it has this little bit, when the reverse reaction is negligible. Again, I alluded to last time that reactions can go both forward and backwards. In Chem 1, we only ever wrote reactions forward, right? We wrote them with a forward arrow. Well, in the next chapter, we will see that sometimes reactions can have double-headed arrows. You'll see them written like that, or sometimes you'll see them written like this, right? But reactions can go forward and backwards. Here, when we're talking about rate laws, though, we're going to say the reverse reaction is negligible. So we're just going to be looking at the forward reaction. So we'll look at the concentration of the reactants versus the rate of the reaction. Next time, right, in our next lecture, we will look at the integrated rate law, and they will express the relationship between concentration and time. Okay, so these are different. The rate law is concentration and rate. The integrated rate law is concentration and time, and you will need to know the difference. Today, we are doing rate laws. Next time, integrated rate laws. Okay, so the rate law is looking at the rate of the reaction versus our concentration, okay? So the rate of the reaction is directly proportional to the concentration of each reactant, right? And just the reactants, not the products. Because again, we're not looking at the reverse reaction. So it only matters how much reactant we have. Lots of reactant, reaction goes fast. Very little reactant, reaction goes slow. Okay, doesn't matter how much product we have. We're only looking at reactants. And they're always going to be raised to some power. Okay, so if we're looking at a reaction where A gives us stuff, right, products. So we only have one reactant here. Our reactant A makes stuff. Then our rate law would have to be, it's always going to say the word rate and then equals K. K is our rate constant, okay, so we just write K. So we are just going to leave that there for now. So we're always going to put rate equals K, and then this will be our reactant, and it's going to be raised to the power of some coefficient. Again, remember these brackets here, these mean molarity, okay? So our rate is directly proportional to our molarity, right, our concentration. This power here, this n, is called the order. It's usually an integer of some kind, and it determines the rate dependence on the reactant concentration. Okay, it's typically a number 0, 1, 2, 3, something like that. And again, K is called the rate constant, and we'll look at how to calculate K as we move forward. So we can always write this rate law which relates the rate to concentration. Okay, so that n that we were looking at, that exponent on each of the reactants, is called the order with respect to that reactant. And if we add up all of the orders, right, we add up all of the exponents, then we will get the order of the reaction. For example, if we look at this one, rate equals K times our concentration of nitrogen monoxide. Oh, and this 2, sorry, this should be a 2 up here, okay? Our rate equals K times our concentration of nitrogen monoxide squared times our concentration of oxygen. So this 2 up here tells us that our reaction is second order with respect to nitrogen monoxide. And the fact that there is nothing here, that tells us that our reaction is first order with respect to oxygen. Okay? And since we have, this 2 and a 1, so total, right, 2 plus 1 gives us 3. So overall, this reaction is third order. Okay. So, like I said, usually this n, this order of the reaction, is a number. We're going to mostly look at things that are 0, 1, or 2. Sometimes you'll get some problems where they're 3, but mostly it will be 0, 1, or 2. If a reaction is 0 order, then the rate of the reaction is always the same. So let's think about this, right? Let's say we had 2 to the 0, right? Hopefully you're familiar enough with math. Anything to the 0 power is always going to equal 1. And if you didn't know that before, you know it now. 2 to the 0 is 1, 4 to the 0 is 1, anything to the 0 is 1. So if our reaction, right, if our number here is 0, if this is 0, then that means that this is a 1. So our rate is never going to change no matter what our concentration is. The rate will stay the same. So let's say we doubled our concentration of A. Well, the rate will stay the same. If we tripled our concentration of A, our rate will stay the same. It doesn't matter what we do to A, our rate will stay the same because it's not dependent on this particular reactant. So if it's 0 order, then changing the concentration will have absolutely no effect whatsoever. If the reaction is first order, then the rate is directly proportional to the concentration. So if we think about this, so let's say our rate is equal to K times A to the 1, okay? If we double A, if we put a 2 in here, right, 2A to the 1, right, that, 2 to the 1 is a 2, right? 2 to the 1 equals 2. So if we double our concentration of A, that will double our rate. Okay, they are directly proportional. So doubling our concentration of A simply doubles our rate. If our reaction is second order, then the rate is directly proportional to the square of the reactant concentration. So let's look at that. So we have, rate is equal to K, and now we have it second order. So if I double A, so if I put a 2 in there, right, 2A, but it's squared, okay, 2 squared is going to make it 4 times the rate. Okay, so our rate will increase by a factor of 4. Our rate will quadruple. Doubling A, because this is second order, right? So we have 2A squared, that's going to increase our reaction by a factor of 4. So 0 order won't do anything to the rate. First order will be directly proportional. If you double the rate, if you double the concentration, you double the rate. If you triple the concentration, you triple the rate. If it's second order, it's proportional to the square. If we double A, then we quadruple our rate, right? If we, tripled our concentration, then it would go up by a factor of 9, right? Because it's 3 squared. So let's look at this graphically. So if we were looking at our reactant concentration versus time, so this one is, this first line here, the purple line is 0 order. Our reactant concentration is going to decrease at the same rate no matter what's happening because it is 0 order. It has no impact, right? Our rate has no impact on our reactant concentration. If it's first order, over time, our reactant concentration, right, is going to taper off, right? It's not going to be decreasing as quickly because our rate is slowing down. Same thing with our second order here. If we look at our rate versus our reactant concentration, if we look at 0 order, right, our rate has nothing to do with our reactant concentration, okay? Our rate is completely independent of our reactant concentration. If it's first order, right, our rate is directly proportional. We're having a straight line relationship to our rate. Our reactant concentration versus our rate is a straight line. And then here, we're having, this slope here, right, this curved line, because it is proportional to the square, okay? All right, let's go ahead and look more at our rate law. Our rate law must be determined experimentally. We can't just look at our reaction and see the rate law, right? We're not using the coefficients. We're not doing anything like that. We have to actually do the reaction, collect some data, and then we can figure out our rate law. We're going to use this method that's called the method of initial rates. And we're going to look at different reactant trials, essentially, and we're going to vary the concentrations of the different reactants, and then we're going to look at what that does to the rate. So we're going to, change the concentrations of our reactants and then look at what happens to the rate. Change the concentration of the reactants, look at what happens to the rate. Because we know if we double our concentration and then the rate doubles, oh, that means it's first order, right? It did the same thing. If we double the concentration of our reactant and nothing happens to our rate, then we know it's 0 order, right? And if we double the concentration of our reactant and our rate quadruples, we know it's, second order. Okay, so we can look at what, when we do something to our concentration, what happens to our rate, and we can use that to figure out the order of the reaction. Okay, so changing the concentration of each reactant will affect the overall rate. And we're going to change the concentration of one reactant at a time. We're going to hold all of the other ones constant so that we can just see what that one reactant is doing to the rate. If we were changing 2 things at once, then we couldn't tell which reactant was affecting our rate and by how much. Okay, so again, we're going to only change the concentration of one reactant at a time. Let's go ahead and look at an example. So this problem says, write the rate law, determine the overall order, and calculate the value of the rate constant K for the following reaction. So we have nitrogen monoxide reacting with chlorine gas to produce NOCl. So here's our experiments. In our first one, we put in some nitrogen monoxide, we put in some chlorine, and we had our reaction rate. Okay, and we did this a couple different times, and we changed up how much of each one we added, right? In the next one, we doubled our amount of our nitrogen monoxide. We kept chlorine the same to see what that did to the rate, and so on and so forth. So we used a bunch of different combinations of these molarities to see how it impacted the rate. So here's our kind of skeleton rate law. We have rate is equal to K times nitrogen monoxide, and we don't know the superscript yet, right? And then times chlorine, and again, we don't know the superscript yet. This is all to figure out what those numbers are up there, okay? So in order to figure out nitrogen monoxide, we need to hold chlorine constant. So you can find any two reactions in which chlorine is not changing. So I picked the first two because they were the first two and chlorine stayed the same. You could totally have used the second, or the, experiments 3 and 4, because again, chlorine stays the same. So you can pick any reactions in which chlorine doesn't change, because then we can look directly at what is happening with nitrogen monoxide. Okay, so in the first two, we have chlorine stays the same, and if we look, the concentration of nitrogen monoxide doubles. If you couldn't figure out, what's happening, if you didn't immediately notice that it doubled, what I would recommend you do is, do one over the other. So I would just do, 0.500 over 0.250, and that gives me a 2. Okay, that doubled. Then you go ahead and you look at the rate, and you see, okay, what happens to the rate over here? Because you might not be able to see what exactly happened. You might see, well, okay, that for sure didn't double, right? Because that would be 2.86 times 10 to the minus 6, but you might not know exactly what happened. So you can say, okay, do 5.72 times 10 to the minus 6 over 1.43 times 10 to the minus 6, and you would see, okay, that increased by a factor of 4. So I doubled my concentration, right? I doubled my concentration of nitrogen monoxide, and that caused the rate to quadruple. It increased by a factor of 4. Okay, so that was 2, that was 4. That means that this is second order with respect to nitrogen monoxide. Okay. So now we can do the same thing and figure out, the order with respect to chlorine. So when we're doing that, we need to find two experiments in which nitrogen monoxide now doesn't change, right? So you could have used experiments 1 and 3. I chose experiments 2 and 4 just because. So you could do, either one. Again, doesn't matter as long as nitrogen monoxide is staying constant. Okay, so when we hold nitrogen monoxide constant, let's look at what happens to chlorine. Okay, chlorine doubles, right? Again, if you weren't sure what happened, just do 0.500 over 0.250. We can say, okay, that doubled. Then we look at what happened to the rate. Okay, the rate doubles as well. It goes from 5.72 times 10 to the minus 6 to 1.14 times 10 to the minus 5. Again, if you didn't know what happened, usually I do big over small. You can do either one. 1.14 times 10 to the minus 5 over 5.72 times 10 to the minus 6. And you would see, okay, that doubles. So this doubled, this doubled. Therefore, since they did the same thing, it's first order with respect to chlorine. So we know that this, right, is a 1. And we don't write 1, so just leave it out. So rate is equal to K times nitrogen monoxide squared, right, because it's second order with respect to nitrogen monoxide, and chlorine just to the 1. Also, I forgot to say this. If you don't know this from math, these 3 dots here, that just means therefore. It's just shorthand. So if you keep seeing these 3 dots, you're like, what are the 3 dots? That just means therefore. Okay, so we did that. We wrote the rate law. There it is. And now we need to determine the overall order for the reaction. That's the easy part, right? Just add up the exponents. So we got a 2 there. We got a 1 there. So our overall order is 3, right? The reaction is third order. That's the easy part. Lastly, we just need to determine the value for K, the rate constant. And you can use any set of data. So I picked the first one because it's the first one. But you totally could have picked any of them. So what we're going to do is we are going to plug in all of these pieces of information and solve for K. So our rate is going to get plugged in for rate. Our nitrogen monoxide will get plugged in for nitrogen monoxide, and our chlorine will get plugged in for chlorine, and we'll just solve for K. So there you go. I plugged it all in. The tricky part here will be keeping track of your units. Okay. So we have our rate is in moles per liter seconds. Also, right, you can write our rate as in molarity per seconds, or you can write it as molarity s to the minus 1, whatever makes you happy. And then we have our molarities, right, moles over liters. Again, you could have written this as molarity either way, totally fine. And then when you do this, right, when you do this math, right, this square will also square the units. So this will end up being like moles squared over liters squared, or even just molarity squared. But you need to keep track of your units. The units for K are always changing, and they're based on the overall order of the reaction. So you need to keep an eye on your units so you can figure out the proper units for K. All right, so once we rearrange this, if we move it to the other side, we'll end up with, I've collected all of my math here, and here's my units. Moles per liter seconds, this was from the rate. And all of these units on this side ended up being moles cubed over liters cubed, or you could have written as molarity cubed, either way. But right now, in this example, I have it as moles cubed per liter cubed. So when it goes to the other side, right, we're dividing by that, so it ends up getting flipped onto the other side. So one of these moles will cancel out, leaving moles squared, and one of these liters will cancel out, leaving liters squared. So we'll end up with liters squared over moles squared per second. You also could have written it as molarity to the -2, s to the -1, okay? If you were to use this molarity cubed, right, it would have been, all of this would be the same, except it would have been molarity per seconds for this rate unit, and this would have been, molarity to the -3. So you have a molarity, to the 1, essentially, times molarity to the -3 will get you molarity to the -2 over seconds, or molarity to the -2, s to the -1. I've written it lots of different ways on the lecture worksheet, so whichever one of these ways to write the units makes the most sense to you, go for it. Okay, they all mean the exact same thing. But the purpose of this slide was to show you how to determine the value for K, right? Just plug stuff in. People are pretty good at plugging stuff in and figuring out the value for K. It tends to be the units that throw people for the biggest loop. So if you have questions about that, please let me know. Oh, and so there it is. Our rate ends up being 9.15. Oh, sorry, this is our overall rate law. Okay, and I know it's a little bit hard to see because I've written all over it, but our rate is equal to our value for K, our units for K, and then we have our, nitrogen monoxide squared times our chlorine. Okay, so all I've done here is taken this value for K and plugged it up into the rate law. All right, what I want you to do here is go ahead and pause. I want you to try these 3 problems out and figure out if you can figure out if you can determine the rate laws for these first 2 reactions, and then the last one is kind of like a fun word problem, if you will, or a logic puzzle. So pause here, try and solve these, and then once you're done, unpause, and I will go over the answer. Okay, let's go over this. So in the first one, right, we need to be able to hold B constant so we can figure out what's happening with A, and then we'll hold A constant so we can figure out what's happening with B. But we're going to have, it'll be rate is equal to K times A to the something times the concentration of B to the something, and we have to figure out what the somethings are. So if we're looking at A, right, we're going to hold B constant. So I'm going to use this one. We'll hold B constant, and A doubles. And if we look at our rate, when A doubles, our rate quadruples. Okay, 0.005 times 4 will give us 0.02. So our rate doubles, our concentration of A doubles, our rate quadruples, which means that it is second order with respect to A. So our rate is equal to K times A squared, and then we'll go ahead and we will hold A constant so we can look at what happens to B. So here we have A is being held constant with experiments 1 and 3. B is decreasing by half, and our rate decreases by half. So since they are doing the same thing, right, they're directly proportional. We decreased our concentration of B by half, our rate decreased by half. That means it is first order with respect to B. So we'll just write B and then no exponent, right? We don't write ones. So that would be our rate law for that equation. All right, let's try the next one. So again, same kind of thing. We want to, hold B constant so we can see what A is doing, and then we'll hold A constant so we can see what B is doing. And again, we're going to have rate is equal to K times A to the something times concentration of B to something. Let's figure out the somethings. So we need to hold B constant so we can figure out what's happening with A. So we'll hold B constant, right? Experiments 1 and 3. And then we'll look, our concentration of A has doubled. And if we look at our rate has doubled as well. That means it's first order with respect to A. So our rate is equal to K times A, and we're not going to write a 1. And then we're going to look at, what's happening with B. So we'll hold A constant, B doubles, and our rate quadruples. So since B doubled and our rate quadrupled, that means it is second order with respect to B. Okay, so the last one is a little bit trickier. This says it's a third order reaction with 2 reactants. So we know that the exponents are all going to add up to 3. So we can have, 0 plus 3, we could have 1 plus 2, 2 plus 1, or 3 plus 0, right? Those are kind of our options. It says if you triple the concentration of one of the reactants, the rate increases by a factor of 3, right? So we're tripling the concentration and it increases by a factor of 3. That should tell you that one of them is first order. Okay, so it can't be this, can't be that. Okay, so one of them is first order, and as you can see, that means the other one is second order. So it doesn't matter which way you want to look at it, right? If one of them's first order, the other one's got to be second order. So it says what happens to the rate of the concentration if the second reactant, right, that one that's second order, is halved. So we can think about it this way. So if we did rate is equal to K, we know that one of them is first order, and the other one is second order. Okay, if we half the rate, half the concentration of the other one, what happens to the rate? Okay, so we have K, we're going to leave A alone, but we're going to half our concentration of B. Okay, well, if we half, right, 1/2 squared will decrease our rate by a factor of 4. So we will quarter our rate. All right, see, wasn't that fun? One more practice problem. This one is a little bit longer, okay? This is like that last example problem that we did, okay? So we have our reactions, we have our concentration, we have our rates. And so what I want you to do is you're going to determine the rate law, just like we did before, figure out the overall order of the reaction, and then calculate the value of the rate constant. So I have the answer down there, but I want you to go ahead and work through it. I just have the answer so that you know whether or not you're right as you are working through. Once you're done, unpause, come back, see the answer. Okay, let's go through this. So the first thing that we're going to do is we are going to figure out the rate law for the reaction. Okay, so we know it's going to be, rate is equal to K times A to the something and times B to the something. And we have to figure out what somethings are. So let's go ahead and we will hold B constant. Here we have quadrupled A, right? And then if we look at the rate has also quadrupled. And again, if you couldn't tell that, just divide them up and see what number you get and see if that matches, right? 0.4 divided by 0.1 gives us 4. 6.24 times 10 to the minus 8 divided by 1.56 times 10 to the minus 8 gets us 4. Okay, so the numbers match. That tells us that it is first order with respect to A. So we know that it's going to be rate is equal to K times A, and then we'll figure out what happens with B. So again, in order to figure out what happens with B, we need to hold A constant. So we hold A constant. Here we have doubled B. And when we have doubled B, our rate has quadrupled. Okay, so again, if you couldn't tell that, go ahead and divide them up. Okay, so this doubled and this quadrupled. Okay, so since, this is proportional to the square of the concentration, we know that it is second order with respect to B. Okay, so that is our rate law. The overall order of the reaction, we're just going to add up our add up our exponents. So our exponent on A is 1 plus our exponent on B is 2. That gives us our overall reaction is third order. Okay, and our last bit is to go ahead and calculate the value of the rate constant K. So when we do this, we'll just plug in our numbers into our rate law. Again, it doesn't matter which one of these reactions you use. I typically use the first one because it's the first one, but you can use any of them that you like. So we're going to plug in our numbers. So our rate is 1.56 times 10 to the minus 8 molarity per second. And that is equal to K, which we're trying to find, times our concentration of A, which is 0.10, and sorry, this is molar, right? These are always going to be in molarities. No exponent on that. And then our concentration of B is 0.10 molar, and that one is squared. Okay, so once we go through and we, do that, we got 1.56 times 10 to the minus 8 molarity per second. And then all of those together will get us 0.0010 or 1.0 times 10 to the minus 3, whatever you like, molarity cubed times K. So now when we go ahead and move that molarity cubed over, we are going to get that K is equal to 1.56 times 10 to the minus 5, and I have it as liters squared over moles squared per second, or you can write it as molarity to the minus 2, s to the minus 1. Either way works. Okay, so that's actually it for today. We've covered a lot of ground. We talked about factors that affect the rate of the reaction. We looked at a way to measure the rate of the reaction as it's going. We talked about how to write a rate law for a reaction, how to determine the overall order of the reaction, and how to solve for the rate constant. So now I would go ahead and find your lecture worksheets for chapter 14 and work through some of these problems. Get really good at determining the order of the reaction, at solving for that rate constant K, and at figuring out the units on the rate constant. Keep working. If you have any questions, please send them my way. Remember, you can send me a message on Remind, and if you reply to that Remind message, it only goes to me. You're not sending it to everybody, so don't worry. You can ask me questions there. You can send me emails. You can post on discussion boards, or you can attend my office hours. However you need to get help, please, please, please ask if you need it. So go ahead, keep studying, and I will see you all next time.